In this video, I will be introducing the idea of indefinite integrals. Previously, we learned that the Fundamental Theorem of Calculus establishes connections between antiderivatives and definite integrals. You may remember that part 1 says if we're given a function that is continuous, then the definite integral from a to x f of t dt is an antiderivative of f. Part 2 of the Fundamental Theorem of Calculus states that if you have integral a to b f of x dx, this could be evaluated by capital F of b minus capital F of a, where capital F is an antiderivative of f. This theorem involves with this idea of antiderivative, which represented with capital F, but you notice we have no notation for this. Because of this reason, we need a convenient notation for antiderivatives that makes them easy to work with. And since the relationship between antiderivatives and integrals given by the Fundamental Theorem of Calculus, we use the notation integral f of x dx for antiderivatives, because this is the same thing as capital F of x, and it means the derivative of capital F, the derivative of antiderivative, is the same thing as the function itself. For this reason, we'll introduce integral f of x dx, and we call it indefinite integral. Now we take a look at an example. We know that we can write integral x squared dx as x cubed over 3 plus c. And we know that we previously learned how to find antiderivatives, and for that reason, it's going to be x cubed over 3. Because all you do is you take x squared, and then you add 1, and then you divide by 2 plus 1. And this gives you x cubed over 3. And if we were to take the derivative of this antiderivative, because this is an antiderivative, or we can call it indefinite integral, because it's the same thing as this left side, we go back to the original function, x squared. Again, here we're explicitly seeing that integrals and derivatives are inverse processes. We need to note that we can regard an indefinite integral as representing an entire family of functions, because we know that we can get many types of functions by manipulating the constant c. So for instance, with the example we're given above, where we have this indefinite integral x squared dx, we know that this is the same thing as x cubed over 3 plus c, and c is a constant that can take many values. That's why this thing, or indefinite integrals, represent family of functions. Now we compare indefinite versus definite integrals. So you notice a definite integral will always have some kind of limit from a to b, f of x dx. And this always represents a number or value. For instance, if you were to give an integral from -1 to +1 x cubed dx, if you do your work, if you calculate this, you're always going to get -15 over 4, which represents area under the curve x cubed. However, an indefinite integral, for instance, integral f of x dx, is a function. In other words, it is an antiderivative. It's always going to represent a function. For instance, if you were to find the indefinite integral x cubed dx, you will always get x to the fourth over 4 plus c. So you guys notice this is a function. But the result of a definite integral is always a number. We know the connection between these two types of integrals were established by the Fundamental Theorem of Calculus part 2. We know that this definite integral could be found by an antiderivative, which is an indefinite integral, evaluated at these values. Because capital F of x represents the antiderivative, which is the same thing as indefinite integral, as we have just introduced that notation. Next we're going to be talking about is, well, now we know that indefinite integrals are same thing as antiderivatives, and we learned antiderivatives before. We learned how to find antiderivatives. The same rules for antiderivatives then should also work for indefinite integrals, because they're pretty much the same thing. So for this reason, I'm gonna go through this table one by one and try to take a look at how these rules work. We're basically restating the table of anti-differentiation formulas that we learned from the previous chapter. So any formula, so now that we know these formulas, any formulas can be actually verified by differentiation of the functions on the right side and then obtaining the integrand. So the first one we have is basically if you have an integral c times f of x dx, because the c is a constant, we can take it out and then write it as this. So you evaluate f of x dx and then multiply it by c. We know that the integral k dx, because we know k is a constant value, so you have a constant function such as the horizontal line 5, for instance. So this will be equal to k of x plus c, because that's the antiderivative for that function k. Sine x is always negative cosine. Integral secant squared dx is always tangent plus c. Secant tangent is always secant. And we know this for sure because we know that the derivative of secant, if you were to take the derivative of secant function, you're always getting secant tangent. For that reason, integral of secant tangent then should give you secant function. If you were to add two functions within the same integral, you're gonna be able to separate them and then add them up. And then here, if you have power functions, the way you're gonna find indefinite integrals, the way you're gonna evaluate that is you apply the rule. So you increase the power by 1 and then divide by n plus 1 and then you add c. Integral cosine x dx is always sine x, because we know that the derivative of sine is cosine. Cosecant squared is the same thing as negative cotangent. Integral cosecant x times cotangent is the same thing as negative cosecant. Alright, now that we know these rules, we're going to take a look at a couple of examples. Example 2. Find the general indefinite integral tan x squared minus 2 secant squared dx. So using the rules that we know, what we can do is we can basically split this integral, because we're subtracting kind of like two different functions. So what we're going to do is we're going to rewrite it as tan x to the fourth dx minus integral 2 secant squared of x. Okay, so from here, because I'm realizing that the 10 over here and the 2 over here are constants, I can take them out. So I can say 10 times integral 10 integral x to the fourth dx plus, you can take out the 2 on the second one, and then say 2 times integral secant squared x dx. And now I reduced the amount of work because all I'm going to do with the first indefinite integral is I'm going to apply the power rule. With the second one, I need to take a look at my table and determine the antiderivative for secant squared, and that is basically tangent. So what I'm going to do is I'm going to replace those things. So it's going to be 10, we keep the 10, and then apply the power rule for this guy, x to the 4 plus 1 over 4 plus 1. And then we're going to say, what I realized is this middle needs to be negative. So here we have negative, so minus 2 times tangent x. And because these guys are indefinite integrals, we have to have a c at the end. Now, you don't have to have separate c's for each of these integrals. If you just have one constant at the end, that is good enough. So then we're going to say 10 times x to the 5th over 5 minus 2 tangent x plus c. We can simplify this and say 2x to the 5th minus 2 tangent of x plus c is going to be an antiderivative or a result of this function. So one thing we make sure that this works is if we were to take the derivative of this result, do we get the original function? Well, for that reason, we can maybe check our work and see if it really works. So what I'm going to do is I'm going to take the derivative of the resulting function I got, 2x to the 5th minus 2 tangent x plus c. So I'm going to take the derivative of this and see if I'm going to get the integrand given in the previous integral. So take the derivative. So we're going to realize that we have, so first we have apply the power rule, 2 times, bring down the exponent, and then subtract by 1. And then minus, keep the 2, and then the derivative of tangent is always secant squared, and then c goes to 0 because that's some constant. So what we get here is 10 times x to the 4th minus 2 secant squared of x. And you guys notice this is what we have started with. So this is basically the original function that is given in the integral right there. So our work is checked. Next example, we have integral cosine theta over sine squared theta d theta. All right, so this is a trigonometric function. One thing that could be useful here is, well, this is supposed to be sine squared. Okay. All right, so one thing that could be useful here is maybe we can try to rewrite the function such that it helps us evaluating it. So the way I'm going to do that is, because the bottom is sine squared, I can rewrite the function as integral cosine theta over sine theta times sine theta, because I know that this is multiplied twice, and this is d theta. Okay. And then what we're going to do next is we take a look at this expression and try to come up with if we can find some identities. So we know that cosine over sine is cotangent, and we know that 1 over sine is cosecant. So what I can do then is I can rewrite this thing as something like 1 over sine. Because this is multiplication, I can have two different parentheses, cosine theta over sine theta multiplied by d theta. So all I did is I kind of split this fraction into two pieces because at the end I'll get the same thing. And so now I know integral 1 over sine is the same thing as cosecant theta times cosine over sine is the same thing as cotangent theta. Okay, so, and then you guys notice the antiderivative for cosine theta times cotangent theta is basically negative cosecant theta. You can verify that by looking at the indefinite integral table, and then all you do is to add c at the end, and then this will give you the result of that integral. All right. So now we take a look at the next example. Evaluate from 0 to 3 x cubed minus 6x. So you guys notice this is a definite integral. This is a definite integral. And we know how to evaluate indefinite integrals using the Fundamental Theorem of Calculus, part 2. Okay? Because we know how to evaluate them from the theorem. And then the theorem states that if you have a function from a to b, f of x dx, you evaluate it using the antiderivative, capital F, evaluated at b and a, which is the same thing as f of b minus f of a. And that's what we're going to use here. So we're going to say our integral 0 to 3 x cubed minus 6x dx is the same thing as the antiderivative for this, which is what I'm going to calculate now. So the antiderivative for x cubed minus 6x is going to be x to the 4th over 4, because I apply the power rule. I keep the 6, so 6 times x squared over 2. So what I'm going to do is I'm going to evaluate this whole thing from 0 to 3. So if you were to work on the inside a little bit, x to the 4 over 4 minus 3x squared. I simplified the second term pretty much. Okay, so what I'm going to do is I'm going to calculate this function, this antiderivative function at 3, and then subtract by at 0. So that'll look like 3 to the 4th over 4 minus 3 times 4 squared. That will be f of 3. Minus, I'll do f of 0, so that'll be 0 to the 4th over 4 minus 3 times 0 squared. 3 to the 4th is 81, so 81 over 4 minus 48. And then we get this needs to be 3 rather than 4. 3 squared. It's gonna be 3 times 3 squared, which is 27, minus 0 minus 0. So we get 81 over 4. So 81 over 4 minus 27. If you were to calculate this, you get negative 6.75. The result of this definite integral then is negative 6.75. So this example, again, we're given a definite integral. We're going to evaluate it at 0 to 12. So again, we're going to use the Fundamental Theorem of Calculus, part 2, to evaluate it. So we're going to do 0 to 12 x minus 12 sine x dx. So we're going to find the antiderivative for this first. So x becomes x squared over 2 minus 12 times the antiderivative for sine is always negative cosine, because we know that the derivative of cosine is negative sine. For that reason, we need negative cosine, and then we're going to evaluate this whole thing at 0 to 12. So then it becomes, well, if we can simplify this negative situation inside, we can see that it's basically x squared over 2 plus 12 cosine x. We're going to evaluate this from 0 to 12. So then we're going to evaluate f of 12, so the bigger value first. So 12 squared over 2 plus 12 cosine 12. And then we're going to subtract by f of 0, which is going to be 0 squared over 2 plus 12 times cosine 0. So 12 squared over 2 is basically 72, because it's 144 over 2, plus 12 cosine 12. We keep it as it is. And then we're going to say minus 0. So basically distribute this negative. And then minus 12 times cosine 0 is 1. So then what we get here is 72 minus 12, because 12 times 1 is 12. We get 60 plus 12 cosine 12. You guys notice cosine 12 is basically a value, right? Because we're evaluating cosine for the degree 12. So if you were to find that exact value using your calculator, you're going to realize 60 plus 12 cosine 12 is going to make something like 70.1262. So therefore, the result of this definite integral is 70.1262. We take a look at this next example. We're going to evaluate the definite integral 1 to 9, 2t squared plus t squared times square root of t minus 1 divided by t squared dt. This is supposed to be dt. All right. So what we're going to do is, because it looks like almost every term at the top has the t in it, it might be useful to basically divide every term by t squared and then try to simplify from there. So what I'm going to do now is I'm going to rewrite this expression as something like 2t squared over t squared plus t squared times root t over t squared plus or minus 1 over t squared dt. So then I'm going to realize that the first term basically becomes just 2, because t's cancel out. And then t squared cancel out on the second one as well. So we have 2 plus root t. And I'm going to rewrite root t as t to the 1/2 for convenience. We don't need parentheses. T to the 1/2. And then I'm going to say minus t to the negative 2. I'm just going to rewrite that fraction dt. Okay, so now I find their antiderivatives because I'm applying the Fundamental Theorem of Calculus Part 2. So the antiderivative for 2 is 2t. I don't need the integral anymore. So t to the 1/2 is basically plus t to the 1/2 plus 1 over 1/2 plus 1. And then the antiderivative for that guy is t to the negative 2 plus 1 over negative 2 plus 1. And I'm going to evaluate this whole thing going from 1 to 9. So I continue doing that. So I'm going to simplify the inside if I can. So 2t plus this thing gives me 3 over 2. I'm going to flip it and write it as 2 over 3 times t to the 3/2 minus bottom we have negative 1, so negative negative makes it positive, t to the negative 1. And I'm going to evaluate this from 1 to 9. Okay. And so again, from here, because I'm evaluating this, I'm gonna calculate f of 9 and then f of 1 and then subtract them. So I'm gonna get, let's replace t with 9 first. So 2 times 9 plus 2 over 3 times 9 to the 3 halves plus 9 to the negative 1. And then I'm gonna say, I'm gonna move this a little bit. And then I'm gonna say minus f of 1 becomes 2 times 1 plus 2 over 3, 1 to the 3 halves plus 1 to the negative 1. Okay, so then I'm gonna continue. So 2 times 9 is 18 plus 9 to the 3 halves is another tricky one. So what we can do is 2 over 3 times, we know that 9 is 3 squared. So here I'm gonna, let me show it here. So this is basically 3 squared raised by 3 halves, which is the same thing as 3 to the 2 times 3 over 2. And you guys notice 2's will cancel, so this will just be 3 cubed. So then we're gonna say 2 over 3 times 3 cubed plus 9 to the negative 1 is basically 1 over 9 minus 2 times 1 is 2 plus 1 to the any power is just 1, so 1 times 2/3 plus 1 to the negative 1 is basically 1 over 1, which is basically the same thing as 1. Okay, so then here I can simplify the 3's over here, so it becomes 2, so 3 squared, so it's 18 plus 3 squared is 9, 9 times 2 is 18 plus 1 over 9. I don't think I need the parentheses anymore. So then I'm gonna distribute the negative here, negative 2, negative 2/3 minus 1. So let's calculate this whole thing. So 36 minus 2 minus 1. So 36 minus 3 is 33, I believe. Let me make sure the whole thing is correct. I think so. Yeah, 18 plus 18 is 36 minus 3 is 33 plus 1 over 9 minus 2 over 3. Let's calculate this whole thing. If you do that, you're gonna get 32 plus 4 over 9. Okay, and that's all for definite integrals.